Hello class, today we will discuss on the following objectives. The first objective would be the index notations. So the index notations are the shorthand notations of any expressions. The second one is the dummy and the free index. These are the two types of the index we have. The third is the outer product and the inner product. The fourth one is that decompositions of a second order tensor. So any tensor that is given to you, that is, tensors can be stress tensors as well as the strain tensors. It can be decomposed into two parts. The first part is known as the symmetric part and the second part is known as the skew symmetric part. So it can be represented as a combinations of two matrices. The fifth part is the Kronecker delta. The index notation. So index notations are the shorthand notations of any expression. So a vectors can be represented by, say, this u is u1 e1 u2 e2 plus u3 e3. So this one is a generalized expressions for a vector that covers both the Cartesian coordinate systems as well as the curvilinear coordinate systems. In curvilinear coordinate systems, we have the cylindrical coordinate systems and the spherical coordinate systems. If we are working in a Cartesian coordinate systems, then we say that the unit vectors are in the forms of I. This E1 will be I, this E2 will be J, and E3 would be K. And if we are working in the curvilinear coordinate system, we say these are the unit rights. E1, E2 and E3 are the unit rights or the unit basis in three directions. So if we are interested in representing this vectors, which is U1 E1, U2 E2, U3 E3, it can be represented in the forms of some kinds of the summations. So we have introduced a symbol that is summations. Here I starts from I is equal to 1 and ends when I is equal to 3. So it can be represented in the forms of a summation that is U subscript I, E subscript I, where I varies from 1 to 3. So the values of I is 1, 2 and 3. So if we are interested in removing these summations, this entire terms, the summations, we need not to write this entire expressions. Then how we can write? We can simply write it U is equal to U subscript I, E subscript I. So in that case we need to give the range of I. So here the range of I would be I is equal to 1 to 3. So the I can take the values of 1, 2 and 3. So we have reduced writing these entire expressions to the simple index notations as these things, where these two equations are the same. This equations or this equations are both same. It is in the this equation is in the general form, whereas this equations or this representation is in the forms of index notations. So we will take an example to illustrate these things. If we simply write U subscript II, here I is repeated twice. We are working with I is equal to 1, 2 and 3. So we will say UII is equal to U11 plus U22 plus U33. So rather than writing all these things, we can simply represent it by U subscript II. So this one is the index notation for this expressions. The second example is when U subscript I, V subscript J and E subscript J. Here we have two types of the index, two different index. First index is I, second index is J, which is repeated twice. So we will break it one by one. First of all, we will break UI. So if we are breaking UI, you will get U1 plus U2 plus U3 subjected to the range of I and J are from 1 to 3. So U1 is represented over here. Now we need to expand these values, which is V subscript J and E subscript J, which is represented over here. Now this J index is a repeated index. Here it comes with V as well as with E. So if we are interested in expanding this terms, we will write it as V subscript 1 E subscript 1, V subscript 2 E subscript 2, V subscript 3 E subscript 3. So we have represented this entire expressions in the index form with simply writing these notations. Sometimes it becomes very difficult to write these entire expression when we are writing in the general form. So we take advantage of the index notations, because by simply writing in the terms of indexes, which is I, j, and it can be k, we can reduce it to a limited number of quantities. So at those locations, the advantages of index notations comes into picture. Now we have two types of the index. First type of the index is known as the dummy index, and second types of the index is known as the free index, or it can be also called as the generic index. So let us define what is dummy index. Thus index, the index which do not appear in the equations after summations is carried out, is known as the dummy index. And the free index are those index, it is a generic index and can have any indicial forms. So we will take an example to demonstrate what is dummy index and what is the free index. If any vectors is represented by a subscript ij, and second vector is x subscript I, here it is a general notation. If we write a ij, this is a tensorial notations which can be the stress tensor, or it can be strain tensor. So x, if I write simply xi, it is a some kinds of a vectors. So all these quantities, the scalars, vectors, comes under the categories of the tensor quantities. So the tensors can be zero order tensors, the first order tensors, and the second order tensors. So a scalar is called the zeroth order tensors, the vectors is denoted by the first order tensors, and the stress and the strains are regarded as the second order tensor. So over here we can see that I is repeated twice. It is with a, it is with x. So I is called the dummy index, and j is only with a, which is known as the free index. Outer product and the inner product, there are two types of the product we do. Different notations are given, different terms, the outer notations and the inner notations representing the outer product and the inner product. So how we define the outer product? It is the product of the two vectors with different index. So for the outer product, the indices has to be different. Here I and j are the different index. So we can represent the two tensor quantities, two vector quantities, by simply writing a. This symbol is known as the dyadic. The cross symbol encircled in a circle is known as the dyadic. A dyadic B. This expression is equivalent to A subscript I, B subscript J. So this symbol is represented by the dyadic. If we simply write this symbol dyadic, we need not to put up the subscript I and the subscript J. If we put simply this symbol dyadic, this means that A has a subscript I and B has a subscript J. So if we expand these terms, A subscript I, B subscript J, which gives us A1 B1, A2 B2, A1 B3, A2 B1, A2 B2, A2 B3, A3 B1, A3 B2, and A3 B3. So if we are interested in representing this entire matrix by in the index forms, then we can simply write it A subscript I, B subscript J. Then we need not to write this entire expression. This entire expressions in the index form is represented by simply these things: A subscript I, B subscript J. The second types of the product we have is the inner product. So what is the inner product? It is the product of the two vectors with the same index. If the index are same, then we will say that we are calculating the inner product. Here I is repeated twice, so it is the same index. So we will take an example here. If A has the subscript I and B also has a subscript I, then by using this we mean A1 B1 A2 B2 plus A3 B3. So rather than writing the entire formulations like this, we can write it in the index forms like A subscript I, B subscript I. Decompositions of second order tensors. The second order tensors are the stress tensors as well as the strain tensors into two parts. The first part is the symmetric part and the second part is the skew symmetric part. So any matrix can be decomposed, can be divided into two parts. The first part is known as the symmetric part and the second part is known as the skew symmetric part. So when we will say that it is a symmetric part, when aij is equal to aji, then this part is known as the symmetric part. And the skew symmetric part, when it is skew symmetric, when a subscript ij is a negative of a subscript ji, then this part is known as the skew symmetric part. So any matrix can be represented as a combinations of the symmetric part as well as the skew symmetric part. So if we have a tensor, second order tensors in the forms of a subscript I aij, and we are interested in dividing into two parts, or we are decomposing into two parts, first part would be symmetric and the second part would be skew symmetric, then this part is a combinations of the symmetric part because aij is equal to aji. So this part is known as the symmetric part, which is written over here. And the second part, when it is skew symmetric, when aij is equal to the negative of aji, then this part is known as the skew symmetric part. So any matrix can be represented as a combinations of the symmetric part and the skew symmetric part, which is known as the decompositions of the matrix. Kronecker delta. The Kronecker delta is represented by this symbol. So it has a subscript I, it has a subscript j. So it can have a values either 0 or it can have a values 1. So when it will have a values of 0, when I is not equal to j. So what are these terms? These are all the non-diagonal terms. So when I is not equal to j, so it is this values, it is this values, it is this values, it is this value, this value, and this values. So at these locations the rows are not equal to the columns. This means that I is not equal to j. At those locations the values of the Kronecker delta will be equal to 0, and also these are symmetrical. So this value will be equal to this value would be equal to this value would be equal to this. So when the values I is not equal to j, it is known as the off diagonal elements. So with these elements are 0. Other value of the Kronecker delta is 1 when the value is 1 when I is equal to j. This means that we are talking about the all the diagonal elements or the trace of any matrix. So what are the trace of this matrix? So these are the all the diagonal elements are the trace of the matrix. So when at these locations the rows and the columns are same, so this value would be 1, this value would be 1, and this value would be 1. Now the properties of the Kronecker delta, as these matrix is symmetrical, then we can say that Kronecker delta ij is equal to Kronecker delta ji. The second properties of the Kronecker delta is that the sum of the trace, sum of the diagonal element is equal to 3. This means that Kronecker delta 1 1 plus Kronecker delta 2 2 plus Kronecker delta 3 3, the sum of all the trace or all the diagonal elements is equal to 3. Now we will illustrate what we have studied till now with an example, with a numerical example. So the problem statement is that for the matrix A subscript ij, so the matrix Aij is given by 3 by 3 matrix, and the second matrix B subscript I is given by this matrix. So two matrices are given to us and we are required to find the following: A subscript II, B subscript I, B subscript I, B subscript I, B subscript j, and A subscript ij multiplied by B subscript I. So let us take first part, which is A subscript II. This means that this is the terms, all the diagonal element terms of the matrix A ij. So what are the diagonal elements of these terms? This value is 1, the second values is 4, and third values is 2. So why we have taken all the diagonal elements? Because the indices in the subscript are the same, so it will be A11, A22 and A33. So if we sum up all these terms, 1 plus 4 plus 2, it will give us a values of 7. Second is when we multiply bi with bi. This means that we are multiplying b1 with b1, we are multiplying b2 with b2, we are multiplying b3 with b3. Why all these terms only? Because we have the same indices, the I index with this and the I index with this b. So we need to multiply these values. So the first values will be 2 multiplied by 2, which is represented over here. The second values will be 4 multiplied by 4, which is 16, and the third value will be 0 multiplied by 0 is equal to 0. So if we sum up all these values, we will get a values of 20. Next is when bi is multiplied by bj. So if we expand these terms, what we will get? b1 b1, b1 b2, b1 b3, b2 b1, b2 b2, b2 b3, b3 b1, b3 b2 and b3 b3. So if we multiply all these coefficients, say take an example b1 multiplied by b1, which is which values? 2 multiplied by 2. What will be b1 multiplied by b2? It will be 2 multiplied by 4, which gives us a values of 8. The third one would be b1 multiplied by b3, which is this values. b1 is this values and b3 is this value. So if we multiply 2 with 0, we will get a values of 0. So if we carry out following formulation for all these coefficients, all these values, we will get all these values. Similarly, we will multiply all these values. We will finally get a matrix of this forms. So rather than writing this as b subscript I, b subscript j, we can write it in the forms of a dyadic forms. If we can simply write b dyadic, this symbol is known as the dyadic, cross enclosed in a circle. This symbol is known as the dyadic. If we are using the dyadic terms, we need not to give the subscript in the forms of I and j. This symbol itself represents b has a first b has a subscript of I and second subscript of b is j. So both these notations are same. This notations and this notations are same. Now the fourth part is we need to multiply a subscript ij with b multiply b subscript j. Over here we can see that I is occurring only once, whereas j is occurring twice. It has the subscript along with a and it has a subscript along with b. So we will first break it into first part, then we will be able to calculate it. So we can, if we are calculating breaking it into first part, it will be ai1 bj, ai2 multiplied by bj, ai3 multiplied with bj. Now in this, j is a repeated index. This means that we will have b has a value b1, it has a values bj is b2 and b j is this values is b3. So put all the coefficients of a I1, this is this coefficient. So which is this coefficient? It is this coefficient, this coefficient. What is a I2? It is this coefficient. This coefficient is the this coefficient represented by this. The third a I3. I3 is these coefficients. Where are these coefficients in aij? So these are these coefficients in ij. So we will multiply all these values. So what are the values of b1? B1 value is 2, which is this value. B2 value is 4, which is this value. And B3 values, this B3, this B3 values is 0. So if we multiply all these matrices, we will finally get a values of this. So the learning outcome for this session is that we have studied about the index notations. So index notations are the shorthand notations of writing any expressions. The index notations are of two types. The first is the dummy index, and the second one is known as the free index, or we also call it as a generic index. The next is when we studied about the outer products as well as the inner product. Next, we studied about the decompositions of a second order tensor. This means that we can divide any tensors into two parts. The first part is known as the symmetric part, and the second part is known as the skew symmetric part. So the second order tensors can be stress tensor as well as the strain tensor. Then we studied about the Kronecker delta and its properties. So this is for this session. We will meet you in the next sessions. Thank you.